In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
Each star you see twinkling in the night sky is a luminous sphere of superheated gas much larger than any planet. And each has a story to tell. A traumatic birth, a life on the edge.
Gravity collects the star in the first place, and then gravity wants to crush it.
And a death that rattles the heavens.
The whole thing goes off in a blinding flash, the biggest explosion in the universe.
The universe at its most volatile and action-packed. Life and death of a star. Like glittering cities in the desert, galaxies arise out of the great darkness of the universe. Galaxies made of billions of blazing lights called stars.
There are billions and billions of stars. In fact, in our galaxy, there are 400 billion stars just in our galaxy.
But how were these stars born? How will they die? And how can it be that all human beings on Earth owe their lives to the deaths of stars? The quest for answers begins here, in a cloud of dust and gas, hovering in the interstellar desert. You are looking at the pillars of creation.
The pillars of creation are a stellar nursery. New stars are in the process of being born in the central regions.
Located 7,000 light-years from Earth, the pillars are part of the Eagle Nebula, which is just one of billions of star-forming regions in the universe. The pillars are towering clouds of dust and hydrogen gas.
If you remember the periodic table of elements from chemistry class, you have the light elements up at the top, hydrogen, helium, lithium, this sort of thing, and then the really heavy ones as you get lower down.
It's hydrogen, the lightest, simplest, most abundant element in the universe, that is the key component of stars. Within a nebula, clumps of this gas and dust slowly coalesce into smaller clouds over millions of years, pulled together by a very familiar force.
The same force that connects us here to the Earth, that keeps us on the Earth, gravity, is the same force that pulls things together in a way that gives us planets and stars and galaxies in the universe.
Gravity, in many senses, is the most important force in astronomy. And when gravity acts in the universe, one of the basic things that it produces is stars. Stars are sort of the most basic unit of mass that is produced when gravity pulls mass together.
Each contracting cloud can produce anywhere from a few dozen to thousands of stars. To form a star like our sun, which is 1 million miles across, it takes a clump of gas and dust 100 times the size of our solar system. These clouds start off their lives bitterly cold, with temperatures hundreds of degrees below 0 Fahrenheit. But as gravity fragments and compresses them, the heat begins to soar. Within a few 100,000 years, the cloud spins into a flattened disk. Gravity coalesces the center of the disk into a sphere, where the heat rises to a scorching 2 million degrees. This glowing system is now known as a protostar. 10 million years later, the searing hydrogen core of the fledgling star soars past 18 million degrees, and something incredible happens. The core becomes so hot it can sustain thermonuclear fusion.
Thermonuclear fusion. It's a lot of syllables, but it just means it's hot there, and small atoms become big atoms.
Hydrogen atoms are moving fast enough that they actually will fuse together and will form a helium atom.
It's this nuclear reaction that produces the energy to power the star throughout its life, giving it a constant source of light and heat.
It's self-luminous, generates its own heat, and that's the essence of what makes a star a star.
If you've got fusion, you've got a star.
Once born, a star's life will be a constant battle, an all-out war against gravity.
Gravity collects the star in the first place, and then gravity wants to crush it. Gravity never gives up. Gravity wants to pull everything together. And so if the star is going to have a life, and a long life, it has to find a way to fight against gravity. You feel gravity all the time when you try to jump or you try to climb a rock. There's always gravity pulling you back down. And in order to fight against gravity, you have to have some way of applying a force which works in the opposite direction of gravity. So if there's a rope, you can use your muscles to pull on the rope and therefore resist and even overcome gravity. But that doesn't mean gravity gives up. Gravity is always working. And so you have to keep applying this force in order to not fall off. And if you give up or let go or the rope breaks, gravity immediately wins and you fall. The same kind of thing happens with stars. Stars are also trying to hold themselves up against gravitational collapse. Gravity wants to crush the star down to the middle.
For stars, nuclear fusion provides the rope in the form of pressure.
The heat gets all the particles in the star moving around quickly, and they bang outwards, and that produces a pressure which can actually hold the star up against gravity. The amount of pressure pushing out on the star just matches the amount of gravity pulling in on the star, and it can sit there and burn happily until something changes.
A star will spend most of its life in this state of equilibrium. It's a phase scientists call the main sequence.
So our sun is in the main sequence. We're very happy it's in the main sequence. It provides us the same amount of energy almost every day. And that's what makes life possible.
All stars on the main sequence aren't alike. Some are much smaller and cooler than the sun. Others much larger and hotter.
So it turns out that how hot something is related to the color of the light that it emits. So a star like the sun, most of the light that comes out from the sun is sort of a yellow type color. If the sun were much hotter, the predominant wavelengths of light would come out into the blue or even into the ultraviolet. And cooler stars emit more red light.
Small, cool red stars like Proxima Centauri, the nearest star to the sun, are known as red dwarfs. They can be as little as 1/10 the mass of the sun, with surface temperatures thousands of degrees cooler. Red dwarfs are the most common type of stars in the universe.
There are many, many more of these sort of very dim red dwarfs floating out in space than there are stars like the sun. Now, of course, when you look in the night sky, you don't see the most common kinds of stars. You don't see these red dwarfs because they're so faint. You merely see the very rare, very bright stars that turn out to be very, very far away.
On the opposite end of the spectrum are the large blue main sequence stars. Averaging a surface temperature of 45,000 degrees Fahrenheit, they can be 20 times the mass of the sun and 10,000 times more luminous. In the life and death of a star, size definitely matters.
Mass is the fundamental thing which drives the life history of a star.
The more massive stars live much shorter lives than the less massive stars. And that's perhaps a little bit strange sounding, because the massive stars have more fuel to burn. You'd think they'd live longer.
So it's counterintuitive that more massive stars will burn through their fuel more quickly than the lower mass stars.
Imagine two gamblers sitting down at a blackjack table. You would expect the one with the most money, the most fuel to burn, would last the longest. But what if the big-time gambler is making huge bets on every hand?
A gambler that is gambling with a lot more money and putting down $10,000 at a time is going to burn through that money much more quickly. And so the more mass you have, the higher temperature, the higher pressure, the higher the fusion rate. And it goes much more quickly with the more mass you have.
And it's always just simply the calculation. How much fuel do you have? And at what rate are you converting it? The high-mass stars live their lives faster. They burn their candle at both ends. It's life in the fast lane. A high-mass star could die within 1 million years.
A star 10 times as massive as our sun might live for only 1/1000th as long. So our sun will live for about 10 billion years in total. A star 10 times as massive as our sun might live only 10 million years in total.
While massive stars have lifespans measured in millions of years, the lowest mass stars measure their lives in tens of billions, if not trillions of years.
Every low-mass star that has ever been born in the universe, and the universe has been making stars for more than 10 billion years, all of those stars are still in their infancy. No such star that's ever been born has ever come close to dying.
But for all stars, including our own sun, life on the main sequence can't go on forever. It can only last as long as the star has fuel to burn. If it runs out of fuel, fusion stops and gravity wins.
Gravity never gives up, whereas fuel, of course, can run out after a while. And so the star and the climber both have this terrible problem that if they don't maintain their fight against gravity, they will end in a death, a cataclysmic death.
Not only does the size of a star influence how long it will live, it also determines how it will die. Massive stars explode from the scene in violent fury, while smaller ones are doomed to slowly fade away. For 5 billion years, our sun, a lower mass, middle-aged star, has been happily burning through its supply of hydrogen fuel, like a gambler slowly plowing through a pile of chips.
The gambler may sit there for a long period of time, just like a star burns its hydrogen for a really long period of time. However, at some point, she's going to run out of money.
Scientists predict that 5 billion years in the future, our sun will reach this critical crossroads. Its supply of hydrogen fuel will have been completely exhausted. Nuclear fusion will cease, and gravity will begin to crush the star. At that point, the situation is desperate. In order to survive, a sun-like star must find a new source of fuel. It has helium on hand, but in order to start burning helium, the core has to be 10 times hotter than it was during its lifetime burning hydrogen.
It won't be able to fuse that helium into heavier elements like carbon and oxygen until the core gets sufficiently hot. And that's because it's harder to get the helium nuclei close enough together for the strong nuclear force to take over, grab them, and cause them to fuse together.
As it continues to contract inward, nature throws the star a lifeline. The core actually becomes superheated by the very gravitational pressure that's trying to crush it. When it reaches 180 million degrees, it can start fusing helium into carbon in a desperate gamble to survive.
So the desperate gambler might go take out a loan on their house and get more money. But in getting more money to burn through, it's really just delaying the inevitable, which is to go bust. And for a star, the inevitable is to die.
The star, which took 10 billion years to burn through its hydrogen, now powers through its supply of helium in a mere 100 million years.
And then the action begins. It runs out of hydrogen, starts fusing helium. Runs out of helium, attempts to fuse carbon and will fail. But all the action what's going on now happens in the last 10% of a star's life.
The searing heat of the helium burning actually causes the outer layers of the star to swell.
At that point, the outer atmosphere of our star will be held in by gravity so weakly that it'll start sort of just evaporating away. Through a series of what I call cosmic burps, it will actually eject the outer envelope of gases, which are only weakly held by gravity. That'll send some shells of gas outward, illuminated by the hot central star. And that will cause what's called the planetary nebula phenomenon. Beautiful shells of glowing gas surrounding the dying core of our sun.
With the core unable to muster any more nuclear fusion, can it possibly survive gravity's crushing grip? As a star the size of our sun dies, it ejects its outer layers. With no nuclear reactions to generate outward pressure, gravity gains the upper hand. The star begins to fall in on itself, like a climber too tired to hold on to his rope.
There's one possibility that the rock climber might be able to use if he gets too tired to hold on to the rope anymore, and that is if he can find a ledge on the rock that he's climbing. Gravity can pull on him all he wants, but the ledge itself will support him against gravity, and he doesn't have to provide any more energy to win his fight. There's a certain kind of star, and our sun is actually an example of this, where the star finds that it has an out in this fight against gravity.
The contracting star finds its ledge in a surprising place: electrons, tiny negatively charged atomic particles.
Electrons don't like being compressed so that they're very close to one another, because electrons effectively don't like each other.
If you compact the electrons hard enough, the pressure of the electrons themselves is able to hold up the star against gravity.
When the core of our dying sun-like star is crushed to about the size of the Earth, this so-called electron degeneracy pressure takes over. Gravity can collapse the star no further. It's left to slowly cool into a bizarre stellar remnant known as a white dwarf. Like this one, Sirius B, which can be seen only faintly aside its companion, Sirius, the brightest star in our sky.
Now, a white dwarf is a very strange type of star. It's very, very dense. The white dwarf has about 300,000 times the mass of the Earth, compressed into a volume the size of the Earth. If you had just a teaspoonful of material, it would weigh several tons. So it's really amazing stuff.
A white dwarf is the final stage in the life of a sun-like star, but it's not quite dead yet. It will continue to shine for billions of years as it gradually radiates away a lifetime of energy.
I like to call white dwarfs retired stars, in the sense that all of the light that they are shining is energy that they accumulated during their normal lives as stars, while they were fusing light elements into heavy elements, as our sun is doing right now. So it's spending its life savings. It's a retired star.
That will be the fate of our sun. But some white dwarfs can have one last hurrah, thanks to a friend who lends a helping hand. Because although our sun is a cosmic loner, more than half of all stars travel through life with at least one companion.
Most stars are members of binaries or possibly even multiple star systems. Close binary stars can have very different fates from your ordinary single stars.
If a white dwarf is gravitationally bound to another star as part of a binary system, it can essentially steal the lifeblood from its companion. The small but dense white dwarf exerts such a strong gravitational pull that it will start siphoning off a stream of hydrogen gas.
If it gathers material from a companion star and it is able to grow in mass, then eventually the mass of the white dwarf can reach an unstable limit, roughly 40% more than the mass of our sun. At that point, the white dwarf undergoes a catastrophic explosion where the whole thing goes off in a blinding flash, what's called a thermonuclear runaway of the entire star.
This mammoth explosion is known as a Type 1a supernova.
So if our sun were to do this, and it won't, it'll die in a relatively quiet way. But if it were to do this, you'd need sunblock or supernova block of a few billion in order to protect yourself from the blinding flash.
University of California, Berkeley astronomer Alex Filipenko is one of the world's most successful supernova hunters. His team has found over 600 of them in the past decade. An incredible feat, considering they occur perhaps twice per century in each galaxy. Searching for supernovas is akin to scanning a crowded football stadium with binoculars in hopes of catching the one person who might be taking a flash photograph at a given point in time.
If you were to look at each person individually, one by one, you would have a hard time finding the person who happens to be taking a flash photo.
Filipenko increases his odds by expanding his search beyond single stars or even single galaxies. To do this, he enlists the help of a very high-tech assistant.
So this is a robotic search engine for exploding stars, supernovae. It has been programmed to robotically take photographs of over 1,000 galaxies a night, and over the course of a week it does 7,000 or 8,000 galaxies, and then it repeats the process, comparing the new pictures of each galaxy with old pictures. Now, usually there's nothing new in the new picture, but occasionally a star blows up, a supernova goes off, and then you can see in the new picture a bright point of light that wasn't there in any of the old pictures. Though a supernova is visually very, very bright, the visible light is only 1% of 1% of the total energy, 1/10,000th of the entire energy emitted by this colossal explosion.
Although Type 1a supernovas come from exploding white dwarfs, many others, known as Type 2 supernovas, signal the dramatic deaths of much more massive stars, perhaps 8 or 10 times more massive than the Sun. Unlike their smaller cousins, when massive stars exhaust their hydrogen fuel, they have the raw power to start fusing other elements. The ashes of each set of nuclear reactions become fuel for the next, so that near the end of its life, a massive star resembles an onion in cross-section, with an outer layer of the original fuel, hydrogen, surrounding layer after layer of heavier and heavier elements.
It goes through its normal life, fusing hydrogen into helium, then helium into carbon and oxygen, then oxygen into neon and magnesium, and then silicon and sulfur. And then iron. The massive star builds up a core of iron. The fusion of iron into heavier elements doesn't do the star any good. It doesn't keep the star hot inside, because fusion of iron into heavier elements requires energy. It absorbs energy. It doesn't liberate energy. So the iron core builds up without fusing and eventually becomes unstable. When it reaches something like 1.5 times the mass of our sun, it collapses.
And the collapse is violent. Within half a second, a core the size of the Earth is crushed into an object roughly 10 miles across. For a moment, the collapsing core rebounds, smashing into the outer layers of the star and kicking off one of the most massive explosions in our universe since the Big Bang.
The collapse of the iron core blows apart the rest of the star in a colossal explosion. It's truly an amazing, incredible event.
Scientists are convinced that supernovas mean much more to the universe than spectacular light shows. They are, in fact, the source of the heavy elements that make up everything around us.
All of the iron in this foundry came from exploding stars, from gigantic explosions. All of it. All the iron you see everywhere came from exploding stars. And in fact, all the elements heavier than iron, directly or indirectly, were made by exploding stars. And those elements were ejected into the cosmos by these gargantuan explosions.
As material from these explosions spread out through the universe, it became the stuff of planets, moons, new stars, and something even more extraordinary. If you could trace your ancestry back to its earliest reaches, you would find an exploding star in your family tree.
We are essentially made of star stuff, or stardust, as Carl Sagan used to say. The elements in your body, not just generically, but specifically, the elements in your body, heavier than hydrogen and helium, came from long-dead stars. The calcium in your bones, the oxygen that you breathe, the iron in your red blood cells, the carbon in most of your cells, all those things were created in stars through nuclear reactions and then ejected by supernovae. And the heaviest elements, iron and above, were produced by the explosions themselves, by the supernovae.
While the explosion of a Type II supernova showers the universe with heavy elements, the core of the exploding star is left intact. Destroying that is gravity's job. But to crush the core any smaller than the size of a white dwarf, it will have to overcome that strange force, electron degeneracy pressure.
Gravity actually finds a way of defeating that tendency the electrons have to push each other apart by combining the electrons with the protons and turning them into neutrons. You now have an object which is made almost entirely out of neutrons, and gravity wins. It now allows the system to collapse. Further, there are no longer electrons stopping that, and gravity seems to win, except neutrons, it turns out, also don't like each other, and you end up with a new stable object, even smaller, even more dense, called a neutron star.
Compared to normal stars, neutron stars are cosmic pebbles. They can be as small as 10 miles across.
So imagine you take a star about 1.5 times the size of our sun, and then you compress all of that material down into a very small space, about the size of Manhattan. You've just made yourself a neutron star.
Squeezing that amount of mass into such a small space makes for an extremely dense object. 1 teaspoonful of neutron star material would weigh 1 billion tons.
Neutron stars are some of the most exciting and weird objects in the universe that astronomers study. If a human being were to stand on a neutron star, it would be a somewhat uncomfortable experience. On Earth, if they weighed about 150 pounds, on a neutron star, they would weigh something like 10 billion tons. Our biology can't stand that amount of pressure, and so a human being would essentially be squashed flat against the surface of the star. In addition to that, neutron stars are spinning at an incredibly high rate, hundreds of times per second in some cases.
It's this rapid spin that enabled astronomers to first identify neutron stars.
Some neutron stars are spinning really rapidly, and they have a really amazingly high magnetic field. That magnetic field, together with the spin, forces a bunch of charged particles, electrons, to go along the axis of the magnetic field. And those accelerated electrons give off light. They produce a well-focused beam of light. Now, this is like a lighthouse whose beam is always on, but you only see it when the lighthouse beam intersects your line of sight. In a similar way, we might see the shining neutron star only when the beam points at us. That object is called a pulsar.
Some stars are so massive, perhaps 25 or 40 times the mass of the Sun, that not even a neutron star can hold up under the weight of their collapse. And gravity will crush them even further into an object of infinite density and almost equally limitless fascination, a black hole.
In some sense, a black hole represents the ultimate death of a star.
A black hole is basically gravity's victory over mass. It is complete collapse of a star, a very massive star.
This collapse creates a region of space where matter is compressed into such a high density that its gravitational field is inescapable.
Black holes are remarkable in that nothing can escape from them, not even the fastest moving thing we know of, which is light.
You shine a flashlight beam up, and even it won't leave. The beam will curve back around, so you won't be able to see it from the outside, hence the name black hole. A common misperception is that black holes just go sucking up everything in the universe. Like that, just like cosmic vacuum cleaners sucking up everything in their vicinity. That's actually not true. Now, objects that are very close to black holes do get sucked in. But if you're comfortably far away with the proper trajectory, you won't get sucked in.
Scientists have long suspected that there is yet another class of supernova involving even bigger stars and even more powerful explosions. Stars that collapse so catastrophically that they leave behind no remnant, not even a black hole. But no one had ever seen one until now. Even after billions of years, the universe is still surprising us with its raw power. In the fall of 2006, astronomers observed the largest stellar explosion ever witnessed by man. 240 million light-years away from Earth, a massive star blew itself apart. Alex Filipenko and his team at the University of California, Berkeley were amazed at the power of the explosion.
And the total energy emitted was 100 times as much as the energy of a normal massive explosion. It's an amazing, really powerful explosion.
A normal supernova comes from the explosion of a star 10 times more massive than our Sun. Incredibly, supernova 2006 GY, as astronomers have dubbed it, seems to have signaled the death of a star 150 or even 200 times more massive. That's about as massive as a star can get. Scientists are still studying the aftermath of the explosion, but they think supernova 2006 GY has a lot to teach us about the first stars that populated our universe.
We actually think that the first generation of stars tended to be really massive, and they probably exploded by this mechanism.
It's these mega explosions that likely seeded the early universe with heavy elements.
These extremely massive stars are the largest iron factories in the universe. A single star, 150 times the mass of the Sun, can produce 20 or 25 solar masses of iron. It's incredible.
In the cycle of life, not only here on Earth, but in the cosmos, as stars die, particularly those that die spectacular deaths, the high-mass stars that manufactured heavy elements in their cores, those give the seeds of the next generations of stars that then increase the likelihood that that next generation will have planets, and planets that contain the ingredients of life itself.
Supernovas aren't the only energetic events in the life and death of a star. Right now, across the universe, there are 1,000 pairs of stars engaged in brilliant dances of fire. For some, this dance will end in catastrophe. astrophysicist Joshua Barnes of the University of Hawaii studies what happens when stars collide.
We don't have the luxury of watching stars collide. A pair of stars, as they draw close enough to collide, would just be a single dot of light, even in the largest telescopes that we have. So we need to investigate these things with a computer.
Using computer models, astrophysicists can take any two types of stars and find out what happens if they become involved in a stellar smash-up.
The models pose hypothetical situations and then see what happens. And you could sort of imagine this is like studying collisions of cars, and you were taking them out and smashing them together in the parking lot, one after the other, to see what came out of them.
Among the most explosive collisions modeled by astrophysicists is the clash of two orbiting neutron stars.
Typically, they're bound together as a pair orbiting one another, and as they orbit, they disturb the space-time around them and create waves of energy. And the energy to do that slows the stars down so they get closer and closer together. As they get really close together, they're orbiting around hundreds or even 1,000 times per second. The final event is very dramatic.
When two neutron stars collide, they're moving at nearly the speed of light. Although the final collision takes only a fraction of a second, it unleashes more energy than the sun will generate in its entire lifetime. Thanks to computer modeling, we can also predict what would happen if a highly dense white dwarf collided with our sun. It would be a frightening collision.
When it got close enough, the gravitational field of the white dwarf would start to distort the sun, so the sun would no longer remain a sphere. It would sort of turn into an egg shape as this thing came close.
As the white dwarf plows into the sun at supersonic speed, its gravity would send an enormous shock wave throughout the star.
And that would produce so much thermonuclear energy to essentially explode the sun.
Amazingly, it would take only about an hour for the white dwarf to plow through the sun and annihilate it. If this scenario came to pass, life on Earth would be doomed. Fortunately, the chances of this happening are slim because the sun is in a very uncrowded part of the Milky Way galaxy.
Individual stars are kind of jostling and weaving as they make their great circuit around the galactic center. So it's a complicated traffic situation, but because the space between the stars is so great, there's not much chance of a collision. If you were to wait out here on this beach until you saw the collision between the sun and another star, you would wait a long time. Even over its entire life, the sun has probably 1,000,000,001 chance of colliding with another star.
But there are places within galaxies where the odds of a collision are much greater. Regions where hundreds of thousands or even millions of stars are crowded together by gravity into a globular cluster. Compared to the spiral arms of the Milky Way, a globular cluster is like a demolition derby. The odds of two stars colliding in the spiral arms of our galaxy are only about 1 in a billion. But within a globular cluster, stars are packed 1,000,000 times more densely than elsewhere in the Milky Way.
In the Milky Way, everybody is pretty much going in the same direction. But in the globular cluster, there's no organized motion. They're basically all orbiting around the center on orbits which are aligned in all sorts of different directions. So some are going one way, some are going the opposite way.
In these crowded, chaotic conditions, stars collide on average once every 10,000 years. Every star in a cluster was born at roughly the same time. So when astronomers look at an old cluster, they don't expect to see any young stars. But strangely, a globular cluster usually conceals some mysterious strangers. Large blue stars, far younger than the small dim stars surrounding them. These seemingly impossible stars are known as blue stragglers.
The mystery of blue stragglers is that they're, in some sense, younger than they have any right to be. All of the stars of that mass and that luminosity would have died off billions of years ago in these clusters. So the puzzle is, where did these things come from? How did they get into these star clusters?
Astrophysicist Joshua Barnes thinks he knows the answer. He believes blue stragglers are the result of collisions between older, dimmer main sequence stars.
A collision of two main sequence stars, two sun-like stars, is actually relatively gentle.
The mutual gravity of the stars locks them in a spiral.
They've lost energy of motion, and they will come back and have multiple subsequent passages. They heat up and swell up and kind of spiral around each other, making several passes, each closer than the last one, until they finally come together and stars merge.
In the end, rather than triggering a catastrophe, the two stars merge to form one more massive star.
What you're basically doing is taking two small old stars, piling them together to make one star now, which is twice as massive, and therefore being more massive, it's brighter and bluer than the rest of the stars in the cluster. So it seems to be straggling behind the rest of the stars.
While the mystery of the blue stragglers seems to have been solved, the heavens are bursting with unusual objects that dare science to explain them. Black holes, neutron stars, and white dwarfs all represent the end of remarkable stellar lives. But there are other strange celestial objects that never got a chance to shine. Not quite planets, not quite stars. These are the brown dwarfs.
Brown dwarf is basically a failed star.
University of Hawaii astronomer Michael Liu searches for these elusive objects.
Stars produce a lot of light. They're very easy to see a long ways away, but brown dwarfs are very low temperature, and so they emit very, very little light. Because they're so dim, it means we can only see them if they're very close to us.
A brown dwarf has the same ingredients as a star, but it simply doesn't have enough mass to sustain nuclear fusion.
If something is born with less than 8% the mass of the sun, then it can't produce its own energy. It's essentially a failed star.
Without fusion, these failed stars start to act more like planets.
If you were flying in a spaceship across the surface of a star, you wouldn't really see anything that looked like clouds or mountains or anything like that. When you go to a brown dwarf, things begin to change.
We think their atmospheres in some ways might be similar to things like very massive versions of the planet Jupiter. If you're familiar with pictures of Jupiter, you see Jupiter has all sorts of banding structure and clouds on its surface. Although we've never taken a picture of the surface of a brown dwarf, we think brown dwarfs may also have similar cloud structure.
Now, these aren't normal kinds of clouds like we know about on the Earth. You have iron vapor making these clouds, and then the clouds may get thick enough that you get iron droplets raining out of the clouds. Obviously, a person wouldn't want to be there because these are molten iron.
To date, astronomers have located only a couple hundred brown dwarfs, and they still have many questions about these elusive objects. For one, they know some brown dwarfs have disks of dust and gas around them. Might those disks form into planets? That's just one of many mysteries yet to be solved as we continue to probe the stars. But already, science has revealed the universe to be a magical realm of dwarfs and giants, stragglers and supernovas. And hidden within the explosive life story of stars, they have found the very history of the cosmos and a key to understanding our own origins.